Okay, we have talked about lots of different things about circles, but today we're going to talk about inscribed. Now, the word inscribed means that it is inside of something. So the word scribe means to write or draw. So if I say something is inscribed, it means it's drawn in. So anytime you see the word inscribed, you can think of that meaning drawn inside or drawn in. So an inscribed angle is an angle that is drawn in a circle. I have an inscribed angle here that is orange. This inscribed angle, you can tell it's inside the circle because all 3 points of an angle are on the circle. So if every point of a geometric figure is on the edge of a circle, we call it inscribed. So there's an inscribed angle. Now, this angle I have in blue here is a central angle. We learned about these a couple days ago. So the central angle is the angle in the middle of the circle, where the center of the angle, the middle of that angle, is in the middle of the circle. Now, just to make things easier to talk about, we're going to label a few things here. We'll call this A, we'll call this B, we'll call this C, and we'll call the point in the middle O. So it is true here that angle AOC, this central angle, is 80 degrees. And it is a central angle. It is also true that angle ABC is 40 degrees. And it is not a coincidence that ABC is half of AOC, because it is always true that the inscribed angle will always equal 1/2 times your central angle. Or you can think of it as being 1/2 times the arc it catches. Because what we learned a couple days ago is that if this central angle is 80 degrees, this arc here is 80 degrees. So I have a central angle of 80 degrees, an arc of 80 degrees, and then the inscribed angle is half of that 80 degrees, or whether you're talking about the 80 degrees of the arc or the 80 degrees of the central angle, it's all the same. If they share the same 2 endpoints, the inscribed angle is going to be half of that amount. Now, this is probably the normal way to look at those, but I'm going to show you a few other ways these can show up. Let's erase the writing we have here so we have some room to work. And what you will notice is sometimes you will actually have this thing in different locations. So you'll have it, for example, you might have the inscribed angle like that, and you're like, hey, that looks kind of weird. Well, since they still catch the same arc, you notice the 2 angles still catch the same arc, that's still an inscribed angle, and it's still 1/2 of the central angle. Now, you can notice it does not matter how I move this vertex along the circle. The inscribed angle, sometimes you'll see them lined up like that, where it actually looks like that the central angle and the inscribed angle are forming a core in line with each other on the diameter, but you still notice the inscribed angle is half that central angle and half that arc of 80 degrees, and so on. Then, of course, it makes no difference also if the size of this angle gets bigger. Like if this angle gets bigger here, you notice the central angle gets bigger as well, and it's always twice as big. So right over here, I have a huge central angle of 160 degrees, and I have that inscribed angle is 80 degrees. And what this leads us to is eventually to make that a right angle, to make that inscribed angle a 90-degree angle, I'm going to have a diameter of the circle. It's going to be hard to get it exact, but that's the basic idea, that if it's 90 degrees, it's going to be 180. So if it's a 90-degree angle in the corner, if it's a right triangle, that's going to have to be a 180-degree central angle there, which you notice I have just created a right triangle in the circle, which is the next thing we're going to talk about, some inscribed polygons. An inscribed polygon, once again, is a polygon where every vertex is every vertex is on the edge of the circle. So the polygon itself is inside the circle because every vertex is right on it. So this is an inscribed triangle here. And over here I have an inscribed quadrilateral, where every vertex is on the circle and the polygon itself is completely inside the circle. So that's what it means to be inscribed. Let's erase those marks I just made and talk a little bit more. Now, we kind of just led into this. What is true is that if you have a right triangle inside of the circle, if it's a right triangle, then you know that the hypotenuse is a diameter. It's not just equal to the diameter, it is the diameter of the circle. And that's true of any right triangle inside the circle. You know that long side, that hypotenuse has to be the diameter. Now, what this means is if it were not a right triangle, it would not have be the diameter there. For example, now let me show you, this is the normal way for it to look, but sometimes you will see that they'll make the triangle really small, still a right triangle. They'll pull it all the way over here, still a right triangle. Doesn't matter what kind of the other angles are. The other two angles, of course, will have to add the 90 degrees between them to make it 180. But as you move that around, notice that that hypotenuse is still the diameter and the angle touching the circle is 90 degrees. And I think there's one of these that will let me show this. That's evidently not the right one. This one, doesn't matter how you turn it. You might see it rotated this way or that way. If you're talking about the diameter of a circle, that is a right triangle. Now, on this side, we have a quadrilateral. We don't know as much about the quadrilateral, but what I want you to notice is this arc I have marked in red and this arc I have marked in green. Between the two of them, they make the whole circle. So the red plus the green, the two arcs, is going to equal 360 degrees. So what that means is the angles that inscribe those arcs are also going to have to add to half of 360. For example, I'm going to mark this 115 degree angle in green because it catches the green arc. And I'm going to mark this in red because it catches the red arc. So I know that this angle here and this angle there, since between the two angles they catch the entire circle, I know that those equal 180 degrees. Now I have these angle measures marked here, so that's really easy to see. But let me get rid of some of these markings so far and show you something else. Even if I was talking about the ones I do not have marked, for example, if I said that this is my red angle, the arc over here would be all the way from here to here because that inscribed angle would go with that arc. And let's do this other one in green. This angle would go from here to here, and that would be this piece of the circle. So I've used the other two unmarked angles. And for just knowing what we're talking about, we'll call this A, B, C, and D. We already said that B plus D was equal to 180, but it's equally true that A plus C is equal to 180. And the mathematical way of saying that is to say that the opposite angles of an inscribed quadrilateral, I apologize for my handwriting on this screen, quadrilateral, are supplementary. And supplementary is just a fancy way of saying add to 180. So complementary. Trying to talk and spell at the same time is a challenge for me today. So opposite angles of an inscribed quadrilateral are supplementary. So it doesn't matter which pair of opposite angles there are, they're going to add to 180 degrees. They're going to be supplementary. So that's going to be useful in solving some problems. Give me just a second and we will look at a couple together. Okay, one thing we can do is we can figure out a lot of information about this here. We have a right triangle here. So let's imagine that this side of my triangle is 6 and this side is 8. And just for no labeling, let's call this ABC. There's a lot of things. We'll call this in the middle circle O. So one thing you could do is it could say, what is the length of BC? Or they could be fancy and they could say, what is the length of the diameter? Well, to find BC, what I can notice is that since it is a diameter of my circle, it goes through the center, this has to be a right triangle. Even if this was not marked as 90 degrees, I would know it was a 90-degree angle because it has to be a right triangle here. I'm marking in green since the hypotenuse is the diameter. So what I can do is I can say 6 squared plus 8 squared equals c squared using Pythagorean theorem. Simplify that. 100 is c squared. C would be 10. So BC was 10. Now, since BC happens to be the diameter, not only do I know BC is 10, but I know that BO would be 5. The radius would be 5. One other thing you could potentially do here is it could ask you for the measure of arc BC. The measure of arc BC, you know, is 180 degrees because it is opposite this 90-degree thing. If the inscribed angle is 90 degrees, this arc here is 180 degrees. So there's a lot of different things you could solve on that one. When I look at the next one, I'm going to set it up a lot like number 7, where we're going to say that this side here is 100 and this side here is 65. And so the labeling matches what's in the book. We'll call this A, B, C, and D. So it basically wants you to find the value of the missing angles. Well, what I want you to notice is if I'm going to mark it in some color here, I'm going to use purple this time. So I'm going to mark angle D in purple. And there's the arc opposite angle D right there. I've gone over in purple. And angle B, I'm going to mark it in a different color. Let's use blue. Angle B, I'm going to mark it in blue. And there's the arc that goes with B. Those opposite angles, once again, catch the entire circle. They catch all 360 degrees. So since they're inscribed and add to 360, inscribed is half of the arc, total arc that catches. So they're going to add to 180. So I'm going to say that angle B plus angle D, which has to be 100, is 180. And that's going to allow me to know that angle B is actually 80 degrees. And if I was looking for angle A, I could use the fact that it was opposite to angle C and basically add those two angles together to 180 as well. So hopefully that'll help you understand inscribed angles and inscribed polygons. If you have any questions, please reach out for help at any time. Thank you.